Okay, hello. So this next topic is going to get reasonably big, so I wanted to break it down and have one video where I sort of conceptually high level explain it, and then the next video where I just code it all out and actually implement it. And this topic is the Vulkan graphics pipeline. Now there's a bunch of different pipelines in Vulkan. We've got graphics, we have got compute, we've got ray tracing pipelines, but I'm just going to focus on the graphics pipeline. Now, this will be very similar to the OpenGL pipeline. The only difference will be that parts of the pipeline which previously were sort of opaque, we now have more explicit control over. Anyway, so I'll just start off with a basic overview of a graphics pipeline. Okay, so sort of ran out of space there at the end, but here it is. So we come in, we have some input that goes to an input assembly, to a vertex shader, through here, then color blend, and then that is written out to the appropriate attachments. So the way the input assembly works is, let's say you throw in a bunch of points. And these points come in this order. So first we get 0, 1, 2, and then we get the same point again. So this is also thrown in as 0.3, this is thrown in as 0.4, then we have 0.5, and then 6, 7, 0.8, 9, 10, 11. I'm doubling up because some points have been thrown in multiple times. It's the job of the input assembler to say, okay, well, what does this mean? If we were rendering in lines mode, it would say, okay, take the first 2 points, stick them together, that's a line, pass that down the line. If it's just rendering in points mode, it just throws them through, no change. If it's in triangle mode, it grabs the first 3 points, throws them down the line, grabs the next 3 points, throws them down the line, and so on. We also have like triangle strips. We grab 3 points and then we grab the last 2 points and the next point. That makes another triangle. But oh, and we also have index buffers. So if we're doing indexed drawing, instead of repeating these points, we just throw the data in once and then read those repeats off from an index buffer. But it's functionally identical down the line. It's the point of the input assembly to make use of these points, this data, and throw it down the line. So anyway, for our example, we go 0, 1, 2. Let's say we're rendering in triangle mode, and then 3, 4, 5 makes another triangle, and so on and so on. So it's the point of the input assembly to make sense of the data which is being thrown at it. Then we have the vertex shader, and what the vertex shader does is, for a given primitive, the vertex shader runs once on each of its vertices, and it's the point of the vertex shader to work out any per vertex data. So for example, attributes such as position, color, and alpha are calculated for each vertex. Now, the next 2 stages are sort of optional. The job of the tessellation shader is, it's fixed, but it's pretty flexible. We can configure it. Is it can subdivide geometry. So we have this primitive, we throw it along, and then the tessellation shader knows about all the points on the primitive, and it can subdivide that space sort of arbitrarily. I'm actually, in my shader programming series, I'm going to be doing some videos on tessellation shaders. They're really cool. We can use them to do sort of mesh subdivisions and get really high levels of detail. And then you can implement level of detail calculations. So you start with a sort of low polygon model and you throw it in, calculate an arbitrary level of detail based on distance, which is basically the stuff that geometry shaders are popular for, but tessellation shaders do them better. But anyway, the geometry shader, what it does is it takes the output of the tessellation shader, and if we don't do anything with that tessellation shader, it's an identity operation, in other words, no subdivision, and it might know extra information, the geometry shader. So for instance, if we were rendering this in triangle adjacency mode, then it would also have reference to the nearby vertices, each of the triangles which are attached here, and we can use that to get extra information. I've got another video coming up on using triangle adjacency in a geometry shader, which is why I'm thinking about that right now. But long story short, the tessellation shader breaks things up. The geometry shader gets all the vertices and sort of runs its own vertex shader again. So we could take this vertex and say, hey, I want to generate some completely random primitive based on that vertex. I'm going to take that and pass that along. That's fine, perfectly fine. Anyway, let's say that didn't happen and we go to the rasterization shader. And as a matter of fact, let's just go as a standard triangle. So the vertex shader, it's maybe not. It's maybe better to put that in there. Okay. So let's say the tessellation happened. The job of the rasterizer is to take this per vertex data and interpolate it using barycentric coordinates, which is basically measuring things inside a shape and saying how close are you to the center, how close are you to the sides. Long story short, it uses rules to interpolate the attributes, and it also performs depth tests and backface culling at this point. Actually, no, the depth test gets performed in the fragment shader because we need to know what's in the buffer. But anyway, it interpolates the attributes, every single attribute, and even if something is sort of off screen, it still gets interpolated. And then we have the fragment shader. And what the fragment shader does is for each of these little pixels, these fragments, it calculates the color which should go on that fragment. So I know I said color over here, but this color is not applied until we hit the fragment shader. So let's say we'll go red and green, and then we look at this fragment here. Well, in the fragment shader, this color has been set for this fragment. It's been stored as an attribute somewhere between red and green, probably yellow, right? But then here in the fragment shader, this is the point where that color attribute is red and applied to that fragment. I know that looks a little bit weird, but hopefully we're familiar with the graphics pipeline already. If you're coming into this video series and you haven't done an OpenGL graphics pipeline, good luck is all I can say. You're going to have a lot more fun. You're going to have a lot better time if you learn OpenGL first and then look at Vulkan. But anyway, then we have color blending. And what color blending is we will have potentially a fragment already set in our color buffer. This is the destination. And then we'll have an incoming fragment. That's the source. And we'll have some information about that. And depending on what our mode is, we might want to multiply those colors. You might want to add those colors. We might want to do the traditional color blending, which is something like destination color is equal to source alpha times source color plus 1 minus source alpha times destination color. Okay, so if I've got a 10% transparency pixel that I'm writing here, I want the output color to be 10% times the incoming color plus 90% times the color that's already there. Hopefully this is familiar, but I'm just kind of re-jogging over it. So there we have it. That's sort of the high-level view. But then we have the question of how do we configure these things in Vulkan? So there's a stage that I've missed, and that is this stage here, which I'm going to call vertex input. And vertex input is the Vulkan API saying, hey, dude, you just threw a whole buffer at me. What does it mean? So we have things like binding descriptions, which are basically the info about the buffer itself that's being thrown at the pipeline. So that is the binding number, the stride, and the input rate. So, for instance, if I have a single vertex buffer which stores the positions, the colors, and the alphas as attributes packed tightly into that one buffer, then they'll all be at buffer binding 0. But if I have separate vertex buffers, so I have one vertex buffer for my position, that'll be binding 0, one vertex buffer for my color, that'll be binding 1, another one for my alpha, that'll be binding 2. That's a bad idea. That's a bad idea because Vulkan is scientific notation. It's designed for really high-level devices and really low-level devices, which means that we cannot have any guarantees, really, on the number of bindings that we can make. Same thing goes for descriptor sets, which I'll talk about in a future video and briefly in this video. But long story short, it's a good idea to group everything together into one buffer. But then within that, we have attribute descriptions. And an attribute description is a bunch of things. It's the location number, it's the binding, I'm running out of space here, the format, and the offset. And this is your traditional attribute pointers from OpenGL. So if I have the position might be attribute number 0 in the vertex buffer, so it'll be location 0. The color will be attribute number 1 within the vertex buffer, so that'll be location 1. All of these will be binding number 0, for instance. And then we have format, which is basically what data format, what numbers are being held there, and the offset. So for instance, color position would have an offset of 0, color would have an offset of some number of bytes, and so on. Hopefully this is familiar. Then we have input assembly, and the primary thing for an input assembly is the topology type. So in other words, are we drawing, if I can spell topology type, okay? So if I'm drawing lines, if I'm drawing points, triangles, triangle strips, whatever. And look, in this video, I'm not going to go in depth in every single option that we can put here. There are other things we can put here, but I'm just going to go through the important stuff. Now, vertex shader, geometry shader, fragment shader. What do these all have in common? They all have shaders. So there's a Vulkan structure called a shader stage, which handles all of these. We specify the type of stage. So for this one, it would be vertex. This would be geometry stage. This would be fragment stage. We have a module, and the module is the compiled shader code. So remember in a previous video, we had the shader code and we pretty much read it and did nothing with it. We compile that, and that goes into what's called a shader module. Then we have it there. And then we have the entry point, which is the name of the main function. So it's tradition to call the entry point main. It does not have to be main. So what we're going to have is these are all going to be specified by these shader stage structures. What we do is we pass in we create the shader stages, configure them, and then pass a bunch of stages into the creation info for the pipeline, which again we'll be doing in the next video where we get more sort of into the weeds on this stuff. Now tessellation, and really tessellation and geometry, if we do nothing with them, that'll just go through as normal with a sort of identity operation. But there are a bunch of other things. So we have a viewport and scissor tests. And these are run before the rasterizer, because the rasterizer needs to have appropriate bounds in order to rasterize. And what this will do is it will sort of clip the view region, so that if we're trying to draw a triangle which is partially on screen, that triangle will be clipped and the full rasterizer won't run. This will speed things up a little bit. Now, why do we have a viewport and scissor? Who knows? But the final viewable region will be the intersection of them. So if the viewport is this region here of the screen that we can see, and the scissor is this region here, then only this intersection will be rendered to. In general, both the viewport and the scissor will be the full screen. So yeah, but let's set that up anyway. And then in the, we're also going to set, some info. We're going to set the depth test and the backface culling. And from memory, this is actually set in the rasterizer. Okay, and I know I said a second ago, yeah, but yeah, I believe that is actually set in the rasterizer, the depth test. So the fragment shader does its thing, and then after the fragment shader runs, we have the option to multi-sample. And what that does is it sort of sets this up in a loop with some sort of internal parameters on the algorithms which are rasterizing. So, you know, when you draw a line, you can potentially, you have a choice of pixels, and depending on sort of some internal biases and parameters and things, you might choose one set of pixels or another set. And then the rasterizer, sorry, the multi-sampling puts the rasterizer on a loop and adjusts the biases to get a bunch of slightly varied positions and then averages those out. So that multi-sampling step is sort of performed after the fragment shader. Okay, and then as I was saying before, we have color blend. So this is just a sort of overview of some of the parameters which need to be initialized to set up a pipeline. But that's not it. That's not all. So we also have some bindings, because we don't just want the pipeline to run. We don't just want the pipeline to run. We also want to be able to pass in some data. So let's say we have our pipeline. It's doing its thing. Data's coming in, data's coming out. Along the way, we want to be able to throw in some uniforms. And uniforms are sort of done in different ways. There's two major ways. There's a push constant. And push constants are pretty much, they work exactly, no, they don't work exactly the same way, but they work very similar to the way uniforms work. You can pass in a small amount of data on the fly. They're great for like one or two matrices. And then if we want to send in larger amounts of info, we also have descriptor sets. I'll talk about these more in a future video, but a descriptor describes a resource of arbitrary type, and then a descriptor set is a set of descriptors. Why do we have a set of descriptors? Because Vulkan is scientific notation. It works with high devices and low devices. Not all devices can bind a lot of things. So get a bunch of descriptors, bind them into a set, bind that set. Anyway, this is what's called a pipeline layout. So a pipeline layout is sort of describing what data the pipeline can take as it runs. Whereas this stuff is just stuff. It's just parameters that we need to specify while we're creating the pipeline. But wait, there's more. in the previous diagram, there's one thing that I didn't mention, and you wouldn't think it's worth mentioning, but it is, and that is, what is this arrow, right? Here the arrow is broken up into a bunch of different stages. Here's the arrow is more defined. This throughput can be visualized as a render pass, and that needs to be specified as well. So here we have it. Let's take an arrow. That arrow is a sort of a single run through our pipeline. That is a render pass. Okay. Now, what we really want to know about a render pass is what attachments are we working with. Some examples of attachments are color, depth. We could have a resolve attachment. A resolve attachment is when a multi-sampled buffer is bounced down to a single sample buffer. So your multi-sample buffer would either be your multi-sample color or your multi-sample depth, and then as after the render pass runs, that is sort of stored in the resolve attachment. What else do we have? Well, let's leave it there for now. Now, each of these is going to have a load operation, a store operation, and then it's going to have a stencil load and stencil store. And it's going to have layout. So it's going to have initial and final layout. Okay, so load operation. What is going to happen when let's go with the color buffer, for instance. What's going to happen when we set up the color buffer for a render pass? We load up the color buffer, we're going to work with it. There's a bunch of different options. We can keep the initial data, the data which was in the color buffer before. Okay, or we can clear it. When we create, one of the things with OpenGL, right, is you have GL clear color. So you specify which color you're going to set as your clear color, and it's similar, right? We have a clear color which we specify for a Vulkan render pass. When we load up a color buffer, we can set it to the clear color. There we have it. That was very well explained. And then what's going to happen with the color buffer when we store it? In other words, after the render pass runs, what is going to happen to that color buffer? Most of the time, we're going to use store here. In other words, remember the color data which you wrote, and we're going to use clear here. So when you bind the color buffer ready to draw, as a default, flush it clear. And then stencil load and stencil store are going to be exactly the same with the stencil buffer. So going with the color buffer, for example, when I do something to the color buffer, what does that do to the stencil buffer? Right? Because we might want to write additional information which we could use in stencil tests and things. Then we have initial layout and final layout. So one of the big concepts of Vulkan is that you have an image, and your image is a bunch of pixels. It's a big array, but the way that data is laid out can be different depending on what we're doing with it. So we might have a layout which is optimal for presenting to the screen. We might have a layout which is optimal for using as a color attachment. We might have whatever. We might have a linear layout. A linear layout is just the standard C++ array layout. Anyway, and the reason for these different layouts is that the data will be sort of accessed in different ways by different architectures, and it might be optimal for different things. Okay, so we have that. And that is our sort of color attachment. But then there's another concept beyond a render pass, and that is a subpass. Okay, so the concept of a subpass might seem a little confusing at first. And the thing that's confusing about it is that we always need to have a subpass. Even though we've got a render pass, we always need a subpass. So again, think of the render pass as the line, and then a subpass is almost like running the pipeline again, running the shader again with data that has come from the previous render pass. The classic example where you might use subpasses is deferred shading, where one pass is done just to capture everything that's visible on screen and write that to a bunch of buffers, geometry buffers they're called, but they're really just color buffers that store arbitrary data. And then that is read in again for like the lighting pass, where we take everything that's on screen and then we light it. This saves time because we are not calculating lighting on fragments which will not be used. But in general, it's very customizable. We can have an arbitrary level of subpasses, but this is the big concept. We always have to have at least one subpass. So I guess, I don't know how many different ways I can explain this. Imagine the render pass is a full throughput from input to output, but that full operation might involve going through the pipeline several times. Okay, so what is important about a subpass is the subpass has attachments. So what do we have? These are just some examples of attachments we can have. We can have color attachments, depth stencil attachments, resolve, and preserve attachments. Now, this might seem a little strange, right? Because we've got these here as well. But think about the attachments are sort of attachments which come from the previous subpass. So let's say we run this and we write some data to the color buffer, which we want to read in subpass 1. So subpass 1's attachments will be the color buffer that was attached to subpass 0. If we want to run something through and keep it, but not alter it, that's a preserve attachment. So let's say I have 2 color attachments here and I only want to work with color attachment 0 in this one, then color attachment 1 will be read as a preserve attachment in subpass 1. But anyway, that's my sort of my crazy rant. All of these things need to be set up in order to create a pipeline. So yeah, in the next video, I'm going to dive in and get our hands wet. We're going to get this stuff done. Okay, see you again soon. Bye.